Hey, hello everybody, and welcome to this session on Protect Your Data from Tampering with Ledger. It's all about bringing the power of blockchain to Azure SQL Database and SQL Server. My name is Peter. I'm a program manager in the data platform security team. That's the team that is managing all the security features in Azure SQL DB, in SQL Server, in managed instance, but also the other data platform services like Cosmos DB, PostgreSQL, and MySQL. And I'm the program manager or the feature program manager for Ledger, and that's why I'm going to talk about this cool new feature that we have inside Azure SQL and SQL Server. Okay, enough about me, let's get started. So, how can you be 100% sure that the data that is inside your database can be fully trusted and that nobody has actually tampered with your data? To give you an example, in my previous life, I was a DBA and I had full system admin privileges on all the SQL servers that my customers had. So I could easily log into a database, go to a table and perform an update. Nobody would have ever noticed that I've changed anything in that table, right? Same for authorized users. If you have power users that have access to your database and they can just easily open a management studio or a data studio and start tampering the data, you will never notice it. Or if you look at, for example, external attackers or malware, if they are able to get to your data, they can also modify your data. So what were the technologies that we had in the past with SQL Server? Well, you could enable auditing, but auditing is good. It gives you the context of what has changed, but it doesn't really give you the tamper evidence, and it doesn't give you really cryptographic proof that somebody has actually tampered with your data. Going back to my example, me as a DBA, I could easily even switch off the auditing functionality, do my modifications, and then switch it back on. Easy. Nobody would have ever noticed it. In SQL 2016, we've also released what we call temporal tables, which keeps track of the history values of your data. But then again, malicious attackers, they can modify or they can play with the history tables and they can even tamper with that history. So we didn't have any real good solutions for proving or making your data cryptographically immutable. Which means that for you as a customer, it's very hard to prove that to external parties that your data can be fully trusted. It's a manual forensic process that costs a lot of money and a lot of time. So this is an issue that we want to address. Secondly, what we also see is that many customers, they're looking into blockchain technologies nowadays. And what we notice is that blockchain, it's good, but we notice that it is sometimes overkill for centralized scenarios. As we know, blockchain is really decentralized, right? And it causes a lot of high latency and it has low throughput because due to the consensus, right? There are a lot of servers in between and technology in between. So you have a lot of latency here. It's also really resource intensive, and some of our customers that came to us, they say, yeah, we want to start implementing blockchain, but it goes against our sustainability goals. We want to go more green. So yeah, that was also an issue that they saw with blockchain technologies. We also noticed that many customers, they're really struggling with starting implementing blockchain technologies in the real production workload. And those customers that manage to do that, what they're typically doing then, they're offloading the data from the blockchain into a SQL DB, for example, just to run reporting on top of that. So we're actually losing the data integrity as well. So on the other hand, we had the auditing issue. And secondly, we have these blockchain scenarios that customers are looking into. Well, our new feature, Ledger, is addressing these two problems. So what is Ledger all about? Well, Ledger is really bringing the blockchain or the power of blockchain into SQL, or the power of blockchain with the simplicity of SQL, sorry. Ledger is really going to make your data in SQL Server tamper evident by using cryptographic. And when I say really cryptographic, it's the same pattern of cryptographic that you would see in blockchain nowadays. Which means that we provide a way for external parties that don't host a database, but that they are still able to have cryptographic proof that the data has not been tampered with, right? We also provide historical record of changes, so who changed the specific row in a specific table, and this can then again be verified through cryptographic proof. This is a new feature, so this is not a new version of SQL Server or a new PAL servers that you need to install. No, it's really inside Azure SQL DB and SQL Server. So we recently announced the GA, so it's general available in Azure SQL DB, and it is available, the feature is available in SQL Server 2022, the CTP version for now. So you can right away start playing with it, right? I also get a lot of questions about my customers. Yeah, what's the cost? Well, this feature is completely for free, except maybe the extra storage that you could have because we need to keep track of your data in a history table. So storage might be an extra cost, but the feature itself is completely for free. All right. Okay, let's jump into a little bit more into detail how ledger actually works under the hood. So what you need to do, you need to create what we call ledger tables. And we have two types of tables. We have updatable ledger tables and we have append-only ledger tables. Typically, of course, updatable ledger tables are used by applications because we need to do insert, update, delete statements. So let's stick to updatable ledger tables for now. Assume that a customer is updating a row in an updatable ledger table. What we're going to do is, first of all, we are going to, let me use my laser here. Where is my pointer? Okay, so a customer is updating the row in the ledger table. First of all, what we're going to do is we're going to keep the old version of that row into the history table. And then, of course, we're going to update that specific row in the updatable ledger table. Now, those who are familiar with temporal tables, they're probably going to say now, yeah, Peter, but we already have that. That's temporal. That's right. And I can even tell you more. Ledger is based on temporal tables. But on top of that, and I'll come to that immediately, we have the cryptographic layer under the hood, which temporal doesn't have. Now, in that history table, we're also going to add extra metadata, not only the row that has been modified, but also, for example, the transaction ID, the commit timestamp, the user that has executed that specific transaction, and so on. So we keep track of all of that. When you create an updatable ledger table, we automatically create the history table for you, but also a ledger view. And the ledger view gives you really a chronicle overview of your database. So it doesn't only show you the current value of your record, but also the history values, right? Now, this is how we keep track of the history of your data, right? But how do we actually then protect your data? Well, it is protected in what we call the database ledger, right? And the database ledger is really a blockchain structure under the hood that is implemented in SQL, right? So each transaction that the database executes is cryptographically hashed, right? By using a SHA-256 hashing mechanism. And all these transactions are then cryptographically linked together, just like a blockchain, right? And that cryptographically hashed database digest, like we call them, they are then representing the state of the database. All right, that's the overview of Ledger, but let's jump in a little bit more into detail how Ledger works. So how does the row hashing actually work? So every row in a transaction is hashed by using Merkle tree mechanism that will create a root hash. So what we're doing is the input of the hashing function is really the row information, like the number of columns, the first column, the length of the column, the type of the column, and so on. And that information is then hashed together. So we have row 1, row 2, and so on, all the rows in a specific transaction. And these are hashed together, like hash 1, hash 2, hash 3, and so on. Now these hashes are then hashed together and it is going to produce what we call a parent hash, which means that in this example here, hash 1 and hash 2, they will be hashed together into hash 1, 2. and hash 3 and hash 4 will be hashed again together in hash 3, 4. And then we move on. So these parent hashes are then hashed together again in another hash. So this will then be hash 1, 2, 3, 4, and so on, until ultimately we produce a root hash that represents all the rows in a specific transaction. Yeah, that's the first step that we're doing. So we're hashing the rows in a specific transaction. That said, what we do next is then we batch all these transactions into blocks. So what that means is that every 30 seconds, we're automatically going to create a database digest file. And well, you can do that, or we are going to do that automatically every 30 seconds if the customer configures that, that automatic digest generation, or the user can also manually generate a digest, right? So basically what we're doing, we're taking the transactions ID, the user identity, the commit timestamp of the transactions, but also the root hash of the update rows, right? The hash that we've just created. And then we're hashing all these transactions again, the same mechanism. So we're using a Merkle tree mechanism. What we're doing is, so we're hashing all the transactions during that time period of 30 seconds together in a root hash or a block, right? And then that block is cryptographically hashed and linked to the previous block, just like in a blockchain, right? And that's how we build the blockchain under the hood. So we're linking the hashes of all the transactions to each other. All right. So back to this slide, which means that once we have then actually produced that block, what we're going to do, or that block also what we call the database digest, we're going to move that outside SQL. So we're going to move that to trusted storage. And what can be trusted storage be? That can be a location like Azure Blob Storage with the immutable settings switched on, or we also have a new service which is called Azure Confidential Ledger. So these are currently the two external trusted storage that we support, right? Now, this is where it comes interesting, of course, because if you have an external auditor, or if you have a scenario where multi-party business processes, an external user can then run a stored procedures, which allows you to verify whether the data can be trusted. So what we're going to do is we're going to take that database digest file from the trusted storage, and in that stored procedure in real time is going to recalculate the hash inside the database. And then we're going to match these two hashes. So the one from the database digest on the storage and the hash that we have just recalculated. And if we have a match between those two hashes, it means that the data can be fully trusted, right? Because we then have evidence, cryptographic evidence, that nobody actually has tampered with the data, right? If these hashes do not match, well, then we also have proof, of course, that our data cannot be trusted. And that stored procedure will then eventually return an error message saying, hey, there is a difference here between the hashes. It will also provide you with the transaction ID that does not match. So then you can start with your investigation what actually has happened. So Ledger makes it really easy for you to prove that tampering hasn't occurred, and that's really, really powerful, right? And you can prove that to external auditors, to even to the court, maybe to, yeah, like I said, multi-party businesses where you need to prove to other parties that your data can be fully trusted, right? Next to the updatable ledger tables, we also have append-only ledger tables, which allows you only to do insert statements. So we actually blocking update and delete statements here, which means we don't need to have that history table, because we just need to have, or we just need to keep track of the append only ledger table. So we just need to keep track of the insert statements. All right, cool. Now, how do you create a ledger table? Well, pretty easy. So it's just a feature, you can start using it. And what you need to do is you need to create a new table, and you need to specify a new option, which is called with ledger equals on. And that ledger table, then you actually create a ledger table. If you don't specify, or you can then also specify whether you want to have an updatable ledger table or whether you want to have an append-only ledger table. That's how easy it is, right? For the database verification, as I mentioned before, you need to run a stored procedure. So we'll make your life also a little bit easier. If you go to the portal and you want to verify your database, there is a button there, and that will show you this specific script here. And what you can do, you can easily copy that script into your Management Studio or your Azure Data Studio, and then just run it, and you will run the verification stored procedure, right? Okay, Ledger has some considerations, right? It means that you can also enable a Ledger database, which means that at that point, all the tables that you create in that database will automatically be updatable ledger tables. I'll come back to that immediately, but it means that once you've switched that on, you can't disable that anymore. So you have a ledger database and you can't revert it into, let's say, a normal database. Same for existing tables. So if you have an existing table and you want to convert it to a ledger table, that's not possible. So you cannot alter it. What you need to do, you need to create a new empty ledger table next to the existing table, and then you need to move the data from one table to another. We also provide you with a stored procedure that can help you with that, with moving the data from the original table to the ledger table. Also the other way around, once you've created a ledger table and you want to convert it back into a regular table, that is not possible. That is not supported, right? Yeah, and like I already mentioned, when a ledger database is created, all new tables will automatically be updatable ledger tables, unless you specify the option append only, right? Then you will have an append only ledger table. We also have some schema considerations. So adding a specific column to a ledger table is supported. The only restriction that we have is that it needs to be a nullable column. So only nullable columns are allowed. Dropping columns is also possible, but we're not physically going to remove your columns under the hood. It's a logical remove, right? Because, and it stays physically, it remains in the database. Why is that necessary? Well, if we need to run the verification and we need to go back in time, we need to have that information, right? So that's the reason why we can't physically remove it, but only logically remove those specific columns. Altering columns is also possible, but the only restriction or consideration is that it cannot have any impact for the underlying data of the ledger table, right? So you can change the nullability, you can change the collation, for example, you can change the length of variable columns, for example, a var character 50, you can change that to a var character 100. That is all supported, but any operation that might affect the format of existing data, that is not supported. So then you will need to recreate the table and then again move the data from one table to another. All right, makes sense? Good. Okay, enough theory, I would say. Let's jump into a demo where I will show you how updatable ledgers table actually works. All right, so first of all, how do you configure Ledger? Well, if you go to the portal and you want to create a new database, we have a new tab called Security. And under Security, there is a new option called Ledger. And by default, as you can see, Ledger is not configured. So if we click Configure, you have two new options here that you can select. The first one is enabling for all future tables, or enable Ledger for all future tables in this database. So as I mentioned before, this is really creating what we call a Ledger database. So when you click this checkbox, all the tables that will be created inside your database will automatically be updatable Ledger tables. So this can be helpful if you, that your database needs to be fully trusted instead of just one single table. This is not mandatory. You can switch this on, but this is not necessary if you want to use the Ledger feature, right? This is only necessary if you want to have a full database Ledger instead of a table. Secondly is the digest storage. So the automatically digest generation that I just explained, you can switch this on here. So when checking this checkbox, You have the two options, as I mentioned, the Azure Storage account or the Azure Confidential Ledger, which is currently in preview. If you select Azure Storage, you can then select an existing storage account, or you can just create a new one if that would be necessary. The container SQL DB ledger digests will be automatically created once you configured the automatic digest upload storage. So these are the only two settings that you can specify in the Azure portal or with PowerShell or with Azure CLI that are related to Ledger. So Ledger Database and the automatic digest upload storage. Right, let's jump into a demo now. We have a company called Contoso, and Contoso has an HR department, and that HR department is using a simple website that shows you or that shows a list of all the employees of Contoso, right? And Rachel is an employee that is working at the HR department, and she's using that application. And as you can see, that list contains a lot of sensitive information. So we have the social security number, we have first name, last name, and we have the salary of each employee of the company, right? Now, there is one also DBA at Contoso, which is Brandon Flowers. And Brandon, he thinks that for the amount of work that he needs to do at the company, and he thinks he earns a lot more. So his current salary is around $55,000, and he says, I want to have some more, or I want to earn some more money, right? Without working more. So let's update my salary. So Brandon is the DBA. He opens his management studio and he goes to the server, because he knows that the Contoso HR database is hosted on this specific server in Azure. Now he opens his management studio, he goes to the employees table, and he executes this specific select statement, and he knows, oh, okay, this is my record here. I have my employee ID, and indeed this is the salary that matches what Rachel sees in her application. So Brandon decides, okay, I want to really earn more, so let's add another 50,000 to my salary here. So let's run this update statement. That's one row affected. Brandon verifies that, and yep, we have $105,000. Now, Brandon thinks nobody will ever notice that I've updated this specific record. And indeed, if we go back to the application and Rachel just does a refresh of the application, she will never notice that somebody actually has changed it. Here, indeed, we have that 105,000 now, but okay, nobody can actually track that. However, Brandon doesn't know that the employees table is actually a ledger table. So if we go here to the Contoso, in the Object Explorer, to the Contoso database, and we go to tables here, and then we have here the employees tables. And as you can see, it's an updatable ledger table. Now, if we click this open, we also have the history table here that you can see. So this is how you can verify in the Object Explorer whether you have an updatable ledger table or an append-only ledger table. Right, so what we can do now is we can use that ledger view, as I mentioned before, which is called Employees Ledger, and we can join this with a new system table, which is called Sys Database Ledger Transactions, to actually jump into the history table and verify what has happened. So if we execute this, we can now actually see what happened. So we have, first of all, we have the commit time of the transaction. We see that the user Azure admin has executed this specific transaction, and this was the record that has been updated. So, and we see here employee ID, Brandon Flowers, and the salary. Now, an update statement is logged in the history tables as two records. So first of all, we save the old version, which is this second record, and this is for us a delete operation, right? And then afterwards, we are going to, of course, update the real record with the new salary. But in the history table, we consider this as an insert statement. So each update statement on the ledger table is in the history table two extra records, one delete and one insert statement. Well, By using this ledger view and the history table under the hood, we can actually see that Brandon has, let's say, tampered. Well, he modified the data, so we are sure that somebody did something. To verify now whether the data inside the database can be trusted, you can run the store procedure. So I just copied the script from the portal, and first of all, what we're going to do is we're going to fetch the digest location, so where are the database digest files stored, and then we're using that location and we're running this specific transaction here, or this specific store procedure, exec sys sp verify database ledger from digest storage, right? So if we run this, sorry, let's run that again. I did a select statement. So as a result, we can see up to which block that we run the verification. And here under the messages, we can see that the ledger verification successfully verified up to block 22. So this proves really this is a cryptographic proof that your data has not been tampered with. Now, to be sure, or to explain very clearly what tampering means, we can see here that Brandon Flowers actually tampered with the data by using the history table, but as a result of the verification, it is successfully. What a malicious DBA, for example, also could do, for example, in SQL Server 2022, is you can directly modify data in the data files without using even the management studio or without using a transaction, right? So you can write directly to the pages, which means that these modifications are then never tracked by the ledger feature. But it can be tracked then by the verification process, because at that point, the hashes will not match, right? The hash from the digest storage will not match with the hashes that has been recalculated in real time. And that's how you can prove that the data cannot be trusted. In this case, since we're using Azure SQL DB, we don't have database files, so it's really hard to tamper with the data under the hood. But by using a combination of this history table and proving that the data can be trusted, Brandon here, he cannot decline that he has not tampered with the data. All right, makes sense? Okay, let's jump back into the slides now. I always get a question of my customers, yeah, Peter, but what about performance, right? If we enable Ledger, we need to keep track of the history table. We need to do the hashing. That must have a performance impact. And yes, they're right. And we did some extensive testing about performance. And first of all, the user workload performance that we did is we did two different types of testing. We did a TPCC test, which is extremely update intensive. And then we also did a TPCE test, which is more common ratio between the reads and the writes. And as you can see here, the performance differ compared to a normal table is 30% impact on a TPCC load due to the high frequency of the updates. If we look at the TPCE workloads, it's less than 7% performance difference. Now, according to the profile data that we collected, inserting the history data into the history table accounts is approximately half of the overhead, while the hashing generation is responsible for the remainder, right? Now, despite the performance degradation compared to a traditional SQL table, Ledger was able to scale up to 72 physical cores on a workstation without running into any bottlenecks and achieve a throughput around or even above 70,000 transactions per second for the TPCC like transactions. So this is more than 20 times higher than what the state-of-the-art of blockchain systems like Hyperledger Fabric can achieve, even when evaluated using simpler transactions. So yeah, it comes with a cost. It comes with a cost because you enable a security feature, but the impact is quite okay. I have also other customers that did a lot of performance testing, and none of them actually were complaining about the performance of Ledger. If we look at more in detail at the DML latency, the overhead that Ledger introduced is the smallest in the case of an insert operation, since we only need to compute the hash, right, of the inserted row, but we don't need to keep track of the history data, right? In case of a delete operation, Ledger inserts the deleted row into the history table and then computes the hash, right? And then finally, for an update statement, as we noticed, we need to compute the hash for each updated row before and after the update. So we need to have the insert of the earlier version and then we need to have first the delete of the earlier version and then the insert of the new version in the history table. So as you can see, updates gets the higher impact on DML latency compared to insert and delete statements. Now, what about the ledger verification, right? Because we need to recalculate the hash in real time. And as you can see here, the verification time is proportional to the number of transactions and row versions that must be processed. So the more transactions you will have, the longer the verification will take. Yeah. Although the verification time becomes high when the volume of the data gets large, it still allows you to process this on a daily basis if necessary, and even if the database stores terabytes of data, right? It is single-threaded though, so there is very, very few impact by running the ledger verification. So it can run in the background without impacting the user workload, even if you upload it to a separate node, such as a secondary replica or a database copy to avoid that, to avoid consuming resources. Now, what are the typical scenarios that we see at customers that are or that want to use Ledger? First of all, streaming the audit processes. Audit processes are expensive and time-intensive activities, and auditing also requires an on-site inspection of implemented practices, such as reviewing the audit logs, inspecting the authentication, and inspecting access controls, right? Although this is still a manual process that can expose potential gaps in security, they can provide a testable proof that the data hasn't been altered, right? So Ledger can help with that because Ledger provides cryptographic proof of the data integrity for the auditors or regulators. This proof can really help to streamline the auditing process, and it also provides non-repudiation regarding the integrity of the system data, right? Now, the other scenario that we see, and I already explained it, is the multi-party business processes. Automating cross-business processes, just like supply chain, and installing trust around them is a critical problem in several sectors, like supply chain, manufacturing, stuff like that. And they're really struggling with the challenge of how they can share and trust the data. So many organizations, what they're doing, they're looking into traditional blockchain systems to digitally transform their multi-party business processes. Now, however, due to the decentralized nature of blockchain, it presents a significant challenge. I already explained it in the beginning, when it is used in real-world production workloads. So there are many scenarios where blockchain solutions are really overkill and doesn't justify the cost and the performance overhead. So Ledger provides a solution for this. The participants or the different parties can verify the integrity of the data, which is centralized, housed in the Azure SQL DB, and without having the complexity and the performance implications of a blockchain network. So it's really having the data is centrally trusted, and the verification is decentralized. What can you do to recover after tampering? So if you run the verification store procedure and you notice that somebody tampered with your data, what can you do to recover and to repair? Well, there are two different scenarios. First, tampering affected the data that is used by further transactions, or tampering didn't affect further transactions. Now, the most straightforward way to repair any kind of tampering is to restore the database to the latest backup that can be verified. To achieve that, of course, you can restore the database to a different point in time, and verify the ledger using the earlier database digests. So the latest point in time that can be verified successfully is the one that guaranteed to not be tampered with, and that can be used to continue the transactions processing. Yeah. Now, this is easy, right? Doing a point in time restore, but there is one important catch. If any transactions that were executed after the tampering has occurred, you will need to accept that, or you lose these transactions, or they need to be manually repaired in the ledger table by reinserting that information for the verified transactions, and then recomputing the hashes for these new transactions that occurred after the first tampering event in the database ledger. Yeah. What happens if tampering didn't affect further transactions? Well, this might be because the attack was detected before any transactions would operate over the tampered data, or because the attack only affected the data in a way that doesn't affect new transactions. For example, if you use a ledger table to store banking transactions details, tampering with details of an existing transaction doesn't impact new transactions, which will work over the current balances. So what you can do is you can actually you can attempt to retrieve the correct table ledger payload for the tampered transactions from a backup file, right? And so you restore the database from a backup file, but you restore it as a new database, where you can still be validated that it is secure, right? And then you can repair the operational database by overwriting the tampered data in the ledger table with the original values. So this means that we're just going to create new transaction recording of the repairing transactions. Here you can see a few customers that are currently using Ledger in production in the finance, supply chain and healthcare industries. We have RTGS Global, which managed cross-currency transactions between banks and records the transactions into ledger tables. We also have Lenovo. They store laptop configuration and specifications in ledger tables to allow customers to verify the integrity of their new laptop and prevent supply chain attacks. And the last customer is Code. It's a customer in South Africa in the healthcare industry, and they are storing medical information about the vaccination status of COVID in the ledger tables. So it makes it easily for them to prove the integrity to auditors and regulators. Now, let's have a look at the Lenovo story. So we have a nice short video about the use case of Lenovo that shows you the value of Ledger in Azure SQL DB.
Lenovo's shipped more than 500 million PCs, and it makes 3 new devices every second. The company wants to make sure that each one reaches its user in precisely the condition and configuration that it left the factory. Maintaining superior levels of computer security is an increasingly challenging task. Since creating its ThinkShield brand in 2018, Lenovo has been examining where it can control potential security gaps related to its device manufacturing and supply chain. We want to be able to show customers that a device hasn't been tampered with and is trustworthy before they bring it into their environment. We want to attest to the device integrity, even down to system levels that require administrator access. To maintain its solid trust relationship with its customers, Lenovo wanted a reliable third party to provide device attestation capabilities. We found an ideal device tracking and attestation tool in Ledger and Azure SQL database, and we used the capability to create our trusted supply chain solution. The Ledger feature enables business partners to establish trust by verifying the integrity of centrally managed data. Ledger eliminates the additional cost, complexity, and performance overhead of decentralized blockchain technology while providing many of its benefits in a fully managed SQL environment. Blockchain is also very resource intensive, which goes against our sustainability goals. It does not have great performance, and it is vulnerable to majority attacks. We found the Ledger technology to be very easy to use. It was just a matter of ticking a box to create a Ledger database with integrity protection enabled. With Ledger, we were able to get both integrity protection and the performance of a relational database. Using a fully managed service like Azure SQL Database also lowers the administrative burden over an on-premises solution. Trusted Supply Chain documents the exact state of 32 different device parameters when a computer leaves the manufacturing plant and uploads the data to Ledger tables in Azure SQL Database, where it's processed and stored. When a customer receives a device, they run a data verification program on it and compare the results to what was collected when the device was shipped, giving a very granular view of any discrepancies. With Azure SQL Database Ledger, Lenovo can prove beyond a reasonable doubt that no one has modified a computer's data, not even Lenovo itself. Moving forward, all new Lenovo computers will be tracked in Trusted Supply Chain. Ledger and Azure SQL Database is a very important building block of our Zero Trust approach moving forward at all levels: data, software, and hardware. We're considering extending it to other high security use cases like continuous firmware monitoring, parts provenance, sustainability, and tracking tax payments and duty transactions. We want to provide end-to-end integrity and transparency to our customers.
All right, to wrap up, where can you learn more about Ledger? We have a bunch of resources, as you can see. We have a white paper, so if you want to read more in detail how Ledger works, you can go to that specific link, aka.ms SQL Ledger paper, where you can download our white paper and read more about Ledger in detail. We have the GA announcement blog post of Ledger in Azure SQL DB. Of course, the official documentation, go to aka.ms/SQL Ledger. The two use cases, the one that you've seen of Lenovo, but we also have another use case of RTGS. The demo that I've used in this presentation can also be found on our GitHub. So go to aka.ms/Ledger demo, and you can download the source code for this and implement it yourself if you want to start playing with Ledger, if you want to show a demo internally at your company, for example. We've also recorded a podcast on Ledger, so if while you're running or while you're in the car, you can listen to our podcast on Ledger. And we've also recorded an episode of Data Exposed with Anna Hoffman, where I explain the same functionality of Ledger like in this presentation. If you still should have questions about Ledger, feel free to drop them in the chat box here. I just want to point out special thanks to Microsoft for supporting this event and supporting the Data Platform Geeks and SQL Server Geeks community initiatives. Well, thank you very much for joining my session. Hope you found it interesting and that you've learned something new about Ledger in Azure SQL and SQL Server. Enjoy the rest of the event. Bye.